So coming off of break, and especially with such a difficult chapter, with so much information in it, I thought it was important to take a minute and review what you know so far about Chapter 9, and also kind of preview what's still to come in Chapter 9. This is to help you get kind of a big picture. So, starting in our tree, we're going to start with geometric series. Geometric series are series where your terms have a common ratio. The sum for a geometric series, even if it's infinitely many terms, is going to be your starting amount over 1 minus that ratio. It converges as long as your absolute value of r is less than 1. So here's an example of a geometric series. Since a is 5,000 and r is 1 over 10, looks like we have a converging geometric series here using that a over 1 minus r formula. You can also have a geometric series where your multiplier is a variable. Here a is 10 and r is x. And so your series converges to 10 over 1 minus x as long as x is between negative 1 and 1. And it doesn't converge to that otherwise. Kind of graphically what that means is here in red I have 10 over 1 minus x. And in blue I have a bunch of terms of that infinite series. And they look a lot alike as long as I'm between negative 1 and 1. Outside of that interval, they don't look anything alike. The reason it's not, these two don't exactly match up is because I didn't use infinitely many terms. I only used 6, I think, or 5. Probably 5 because it looks like an odd polynomial. So that's kind of what convergence means. Then we said, well, if it's geometric and it has x's in it, that's cool, but that's pretty limiting. So we started talking about other ways of writing Taylor series. So to start with, we have the geometric series. That's where you should always start. If you recognize that your function is geometric and you can, that a over 1 minus r format, you say, oh, it's geometric, so a is x squared, r is 2x, I can build it from there. And that's definitely one method. It's limiting, it doesn't work for very many series, but if it works for your series, it's the fastest way to go. This series would converge as long as your r is between negative 1 and 1, so it converges for negative 1/2 to 1/2. The other thing you can do is you can use known series to build. So, for example, if someone asks me to build the power series for cosine of x squared minus 1 centered at 0, I'm not going to start all over. I already know the power series for cosine of x because I took the time to memorize it. Cosine is the even one, so I've got the cosine series memorized. And since I have that memorized, I'm going to subtract 1 from it, so this 1 will go away. And then I'm going to replace all of my x's with x squareds to get my new series. That's going to be a lot faster than starting with the derivatives and going through all that whole process. The other thing you can do is if you recognize that your function that you're trying to build is the derivative or antiderivative of one that you already know, then you can do derivatives or antiderivatives term by term. So for example, if I'm asked to build the power series or the Taylor series for natural log of 1 minus x, I could start doing a whole bunch of derivatives, or I could say, well, I know the power series for 1 over 1 minus x because it's geometric, and I also know that natural log of 1 minus x is the antiderivative of that. So I can term by term take antiderivatives of each term. So the antiderivative of 1 is x. The antiderivative of x is x squared over 2. The antiderivative of x to the n would be x to the n plus 1 over n plus 1. That's going to save you a lot of time, and that's going to be a good tool to use. The fourth thing you can do is you can build from scratch. Building from scratch can be tedious, and it can take a lot of work, but sometimes you're asked to do it. So, for example, if you have a function, f of x equals square root of x, I don't have one memorized for that, centered at x equals 1. Where I would start is I would say, well, my function is square root of x. My derivative would be 1/2 x to the negative 1. I'm just going to go out, negative 1/2. I'm just going to go out to the third degree. I didn't write it in my instructions because I'm just jotting down instructions, but it would be clear from the problem how far you would have to go out. So this would be negative 1/4 x to the negative 3/2, and then the next derivative would be 3/8 x to the negative 5/2. And so if I were writing a third degree polynomial centered at 1, my first term would be, so f of 1 would be 1. So my first term would be 1. My next term would be f prime of 1 would be 1/2. So times x minus 1. My second derivative evaluated at 1 would be negative 1/4 divided by 2 factorial. So I have negative 1/4 divided by 2 factorial, and then x minus 1 squared. And then if I'm doing a third degree polynomial, I'm going to take my third derivative evaluated at 1 would be 3/8 divided by 3 factorial, x minus 1 to the third. I'm not going to simplify my coefficients, but I really want to point out that all of these derivatives that I took were to find the coefficients. When I plug in a number, these shouldn't have x's in them at that point. Those are going to have, I'm going to have a number plugged in. My center should be plugged in. So it's to help find my coefficients. And then the other thing I really want to point out is that this looks like a big bear to memorize, but it's not that bad because this means the nth derivative divided by n factorial and to the nth power. They all match up as you're doing those. So those are Taylor series. Those are 4 ways to build those Taylor series, kind of in increasing order of difficulty. Then we talked a little bit about convergence tests this chapter. We'll do more with that in the future. We have the nth term test, which is for divergence only. If your nth term is not going to 0, then you can conclude that your series is diverging. If your nth term is going to 0, you can't conclude anything. We have geometric series test. Remember that multiplier has to be, the absolute value of the multiplier has to be less than 1. We have a direct comparison test. If you can find a series that is larger than your series but converges, then your series converges. If you can find a series that's smaller than your series and diverges, then your series diverges. There's the ratio test, which is a big deal and one that you will use a lot. The ratio test is saying if I look at just my series, so that's the nice thing about the ratio test. I don't have to come up with another series. If I look at my series and I take the next term divided by the current term, if that ratio is less than 1, then my series converges. If that ratio is equal to 1, then I don't know what happens, and if that ratio is greater than 1, then my series diverges. We can look at telescoping series, so we just write out some terms and see if they converge, see if they kind of cancel out. That's a very specialized type of series, kind of like geometric series are specialized, but if you have a telescoping series, it's kind of nice because you can see that they converge. In the future, we'll talk about the alternating series test, we'll talk about the integral test, and the p-series test, and the limit comparison test. So we have some more convergence tests coming up. Then we said, well, now I have all these great Taylor series, but I don't know what they converge for. So we talked about how to find the interval of convergence for a Taylor series that is just a general Taylor series. First of all, it's geometric. If it's a geometric Taylor series, then you can look at just that ratio. You know the interval of convergence right away. But for any other Taylor series, you take the absolute value of your terms and you use that ratio test. That's why the ratio test is so important. It's how we're going to find the interval of convergence for any random Taylor series. And then what we're going to do in the future, we haven't gotten there yet, but we're going to check the endpoints. So we're going to check what happens if our ratio test gives us a 1. So we'll plug in those x-coordinates that give us a 1 and see if our resulting series converges or not. That's how we'll deal with that in the future. So an example would be this Taylor series, does it converge or not? Or not does it converge or not? It definitely converges somewhere. It's the interval of convergence that we're interested in. So we're going to take the absolute value and we're going to do the ratio test. We're going to do the limit as n goes to infinity of 4 to the n plus 1 over n plus 1 times x minus 3 to the n plus 1 over 4 to the n over n times x minus 3 to the n. And then we're going to kind of subtract exponents to simplify this. So we have 4 times x minus 3 to the 1, and then times n over n plus 1. And we're doing the limit as n goes to infinity of that, and as n goes to infinity, n over n plus 1 is going to go to 1. You could use n behavior, you could use L'Hopital to get to there. And so we have the absolute value of 4 times x minus 3 has to be less than 1. And then we're going to set that up as an interval. So we have 4 times x minus 3 is between negative 1 and 1. So we would divide by 4, so we have negative 1/4 is less than x minus 3 is less than 1/4, and then we'd add 3, so we have a negative 11, 12, whatever, 11/4 is less than x is less than 13/4. And we would check to make sure that our endpoints converge or diverge, because a big part coming up in the future is, should these symbols be straight less than symbols, or should they be less than or equal to symbols? We're not there yet, but that's where we're headed. In this chapter, we also looked at the error if we decide we don't want to use infinitely many terms because it's just not practical. If you have an alternating series, the error is easy, so hope that you see alternating series on your test. The error bound, if you have an alternating series, is just the next term. Your error will be no worse than just looking at the next term. Error is always positive, so you can take the absolute value of the next term. Geometric series, the error formula is also going to be geometric. And then we talked about the Lagrange error bound. This is actually kind of a little deal. You don't have to worry that much about this one. But the two that you really should worry about are alternating series and the Lagrange error bound. If your series is not alternating, then your error, the maximum error you can have is if you look at that next derivative, you want to maximize that next derivative, and z is between x and a. So how can you make that next derivative as big as possible by choosing a z between x and a? And then you just basically do the next term. You do divide by n plus 1 factorial, and you take x minus a to the n plus 1. And that gives you your maximum error. And then coming up, you're going to be doing that interval of convergence where you're checking the endpoints. So you're going to plug in x equal to whatever your endpoints are to figure out what happens with your series. And you're going to be using all of those convergence tests to test the new series with those x values plugged in. And then some tips and tricks that I've noticed about Chapter 9 on the AP test. First of all, don't forget about geometric series. They're the easy ones, so hope that you see some of those. Remember that the error bound for alternating series is easy, so if they're asking you for error, check first that it's alternating before you start doing Lagrange error. Make sure you have the common series memorized, like sine of x, cosine of x, and e to the x. And then two series that just come up a lot on the AP test are harmonic and alternating harmonic. Harmonic is the series 1 plus 1/2 plus 1/3 plus 1/4. It's called harmonic, and it has something to do with music. And I've had students study that in the past because they were interested in it. I don't know much about music, so I'm not going to talk much about that, but this series diverges. Whereas an alternating harmonic series with the signs that alternate, this one converges. And those two series just seem to come up a lot, and so they're worth memorizing, that the harmonic diverges and alternating harmonic converges, and you can use that as a justification. So you can say, this series converges because it is an alternating harmonic, and it kind of saves you having to do those other tests. Alright, so that was a lot of information. It fit into 15 minutes, but barely. Thank you for taking the time to watch this, and I'll see you in class.